Welcome to the TWIML AI podcast. I'm your host, Sam Charrington. Hey, what's going on, everyone? I was just checking my calendar and noticed that by this time last year, I had already been to about half a dozen conferences in 3 different cities. While I don't miss planes, airports, or hotels at all, I really do miss the opportunities that conference visits created for me to really connect one-on-one with listeners and guests of the podcast. Of course, what we're all learning now is that physical separation does not need to mean that we're disconnected. So let's you and I use this as an opportunity to connect virtually. I'd love to hear from you, yes, you, about how things are going for you in these unique times we've found ourselves in. What are you working on? What new routines are you establishing? What new breakthroughs or realizations might you be finding in your work or personal life? Please reach out and let me know what you're up to via text or voicemail to 314-582-5935, via email to sam@twimlai.com, or via a message on our website or your favorite social media platform. I hope you're staying safe and healthy and helping others stay healthy by observing social distancing. And now, on to the show. All right, everyone, I am on the line with Karim Beguir. Karim is co-founder and CEO at InstaDeep. Karim, welcome back to the TWIML AI podcast.
Hi, Sam. It's a pleasure to speak again.
Absolutely. So if Karim's name sounds familiar, that's because we spoke, we were trying to figure this out. It was between a year and a half and a year ago. The show actually was published in September. It was number 302. And you should definitely check it out for Karim's full background. But Karim, why don't you give us a brief overview of what you're up to, as well as an update from when we last spoke?
Absolutely. So first, it's a pleasure to be back and continue our conversation. On our side, it's been pretty eventful. A lot has happened. As you know, InstaDeep is a decision-making AI startup. So we focus on problems related to making complex decisions. We also do our own innovation in AI and try to be helpful to the community. And we've made progress basically on these 3 areas. We've been able to release innovative products in decision-making AI. We've also been able to publish and innovate in research, publishing original, pieces that were actually welcomed at NeurIPS, where we got a spotlight presentation, for example, with Google Deepmind. And we've also been very active on the community side, organizing major events in Africa and helping basically lots of young talents find and seize the opportunities in AI.
That's right. And we most recently saw one another at NeurIPS and had a chance to catch up briefly at the Black and AI dinner, where you really piqued my interest around one of the company's new initiatives or products, which is called Deep PCB. Tell us about what Deep PCB is.
Absolutely. So DeepPCB actually started with a conversation. 2 years ago, I had a dinner with a good friend of mine who is actually an expert in hardware design, worked on chips for well-known phones, etc. And we were speaking about what is AI doing in this particular sector? And he was like, not that much. In particular, PCBs stand for printed circuit boards. So basically, those are the chips that you will find with all sorts of consumer electronics products, iPhones, speakers, Bluetooth, etc. And, the situation in that market was that, auto routers, basically automated systems to connect the different components, build basically the electrical circuitry, have been going on for many years, but they were not that great. And we were like, hey, that sounds like an interesting problem to look at. We started looking into it. Eventually, this good friend, Nabil Shuba, who's now leading our hardware team, joined InstaDeep. And we've worked very hard on this project, and we're very proud, to have been able to achieve our goals. And in November last year, we've released it in beta form, and it is a world first. For the first time, we have an AI system that is end-to-end, fully deployable and scalable on the cloud, capable of understanding how to route chips, essentially.
And now, last time when we spoke, our conversation was focused on the work your company was doing, applying deep reinforcement learning to logistics. Is Deep PCB also based on deep reinforcement learning?
Absolutely. And there is a very strong commonality and design philosophy between our products. So in a sense, let me give you an example. We've continued to do great work in logistics, and recently, last September, we've won a major contract, for example, with Deutsche Bahn, the German railway company. And to give you an idea, this is about routing trains on a large scale. We're talking about 10,000 trains a day, and something on some 33,000 kilometers of railway. But it turns out there are commonalities between routing trains and routing chips on a board. And so we've realized that, the projects and the type of research that InstaDeep is doing is actually applicable to multiple fields. And when it comes to, in particular, printed circuit boards, the opportunity was compelling. So we went full speed ahead, and this turned out to be our first product.
Alrighty. So when you initially met with your friend mentioned that while these auto routers have been in place or have been in use for many years, they were not without their challenges and problems. What were some of those challenges and problems, and what was the opportunity to introduce AI?
I think auto routers have been, there's been a lot of great work done on auto routers, but in terms of design philosophy, the design philosophy is all about essentially using heuristics to solve problems. And we spoke a little bit about this in our past conversation. So it's very similar to, let's say, what was the status of software for chess before AlphaZero came out. Those systems which work very well, actually, but still are built on heuristics. For the hardest problems, heuristics have limits. And a system that can essentially mobilize learning and learning at scale can get better results. When it comes in particular in the status of printed circuit boards, it is actually incredible, and we are in 2020, that actually complex circuits are still designed manually. And the reason why people design those manually is because auto routers essentially fail to deliver the goods to the degree of quality which is expected by high quality customers. So as a consequence, we see a really compelling opportunity with modern AI built on the latest innovation, and some of it actually developed in-house. We actually have patents on the work we've done for Deep PCB. There is an opportunity to accelerate the design cycle of products, because it's not just about quality. Human engineers do absolutely amazing work and have amazing intuition, but it's about the speed. A human engineer could take, in certain cases, multiple weeks, if not months, to completely route a complex board. With modern AI, we do believe at InstaDeep that this timing can be brought to 24 hours. This, if done at scale, would be tremendous for the industry, and it would accelerate the product cycle. We are very used in consumer electronics to have a cycle every 6 months, every year. There's a new version coming. We believe that AI could actually accelerate that cycle, and as a consequence, also make it easier to design new products and experiment, and ultimately unleash more human creativity, mobilizing AI.
You mentioned complexity of the boards as being one of the challenges. What are we talking about when we talk about complexity? I'm assuming we're measuring that in, for example, number of components, but having worked with circuit boards before, there are also issues like the number of layers and things like that. When you talk about a complex board, what exactly are you talking about?
So a board really consists in basically AOIs that we need to connect, and as a consequence, there can be lots of
what that needs to be connected.
So you have pairs of components essentially
Okay.
that need to be connected, and there could be thousands of those. And as you mentioned rightly, they could be multiple layers. Simple designs start with 2 or 4 layers, but you could have a lot more. And the more you have layers, the more components you have to connect, the harder the problem. It is an NP-hard problem. And so this is where AI can help, particularly when you're looking at, the most difficult designs that would take human engineers significant amount of time to solve.
And so, how do you frame this problem as one that reinforcement learning can be applied to solving?
So this is another case of needle in a haystack style problem. So you have an extremely large solution space. To give you an idea, the game of Go was 10 to the power 170 roughly. We are talking here at significantly more. Like this can be very, very large. And so the question is, how can I build a system that's going to figure out what is a good solution to this problem? And of course, you have lots of rules that you need to abide by. We call those DRC, so basically design rules checks that need to be, absolutely verified for the circuit board to be valid and to be deployable in production. So the question is, you have this massive optimization under constraints where essentially you need to find a good solution. And we know from recent progress and from also our own experimentation that AI systems can be built using deep reinforcement learning to build up intuition. So it's a little bit like humans would do it, except that you have the benefits of doing it very consistently and importantly at a very large scale. We're talking about potentially hundreds of CPUs, if not thousands, working together with GPUs to accumulate experience and sort of build up the right knowledge base to crack the problem.
And so, when you talk about this knowledge base, can you go into a little bit more detail into how how you're building the agent and the learner, and how you're kind of representing this knowledge that's being accumulated?
Yeah, so the spirit is very similar to, for example, what has been done by Deepmind for the game of chess and Go. You're going to have a learner that's essentially going to play games. And based on the outcome of those games, is going to start to, learn what works and what doesn't. So you can see this problem as basically having a reward function, which is completing the design. If you've completed the design and it is DRC clean, so it satisfies to all the design rules, then that's a good outcome. And so you are effectively starting, let's say, from a random point, but learning as you go and sort of putting more probability on the paths that are yielding a good solution. And of course, the devil is in the detail on those systems. But if you do this diligently enough, you're going to get a system that's going to start to figure out what it should do, first on small boards and then on bigger ones, and ultimately get you to competitive results.
Now, I would imagine when a human engineer is working on these kinds of problems, there are certainly completion of the board is, a primary goal, but I'm imagining they're also worried about like the total length of their traces, which probably corresponds to noise on the board or latency between components, that kind of thing. In other words, a lot more kind of nuanced characteristics than just whether, all of the components are connected. Are you able to take these kinds of things into account?
Absolutely. So those actually participate into the design of the reward function. So this is the way to look at it. Of course, exactly like you said, it is desirable to have circuit length as small as possible. It is desirable also to have as little as possible changes from one layer to another through what we call vias. So those can actually be expressed in the design of the reward function such that you sort of have everything you need and that the system has everything it needs to learn. But absolutely. And, one of the things, one of the areas where we spent a lot of time was how can we incorporate those into like a functional mechanism that triggers learning. And we're very happy to say that that actually this is possible. And when we look at the first announcement we made in November last year, when we announced the beta release, actually, many engineers came to us and they just couldn't believe that an AI system would go end to end and crack this problem. Yet, this is another proof of how powerful AI can be in 2020, and in particular, deep reinforcement learning applied to decision-making problem is truly disruptive. So at InstaDeep, we are focusing on those type of problems, and we believe there is tremendous value to be unlocked for our customers, and in terms of improving efficiency, accelerating design cycles, and the like.
You described the process as one of starting with simple boards and working your way up to more complex boards. Can you elaborate on that? Is that if you've got a particular problem with a particular set of circuits that need to be connected to one another, is the learner that you're trying to create to route this particular board, is it starting with a subset of components and then gradually increasing the complexity of what it's doing? Or are you referring to kind of building up a knowledge base across multiple, maybe even theoretical, board layouts that you have created just to train the learner, and then you can take this pre-trained learner and apply it to new boards?
It's not necessarily the final algorithm that we designed, but it's more like the approach we took. Like to crack a problem like this that actually many people have tried and failed and this is a good generic principle in deep reinforcement learning. Start with a small problem that is almost too stupid, right? But make sure that it is working. Make sure that what you expect to see is indeed what you see. Devil is in the detail in those systems, and deep RL systems in particular are notoriously tricky to train because a problem could come from multiple sources. It could come from there's like straight out bug into your system, or it could be that you have the wrong initialization parameters from an applied math point of view, and so you're doing everything right, the code is right, but the system still won't learn because the parameters have been badly initialized. So I'm describing more philosophy. We really start with baby cases and built up our skills, expertise, and train progressively better agents, realize what works, what doesn't. So there is a lot of in-depth analysis and details that you need to do to be able to have systems that actually are ready for the real world. And I think that's an interesting problem. This, when we look at the work that the InstaDeep teams do, I think what we're really excited about is how can we take those algorithms that have been tested mostly on games, on very well-defined environments, if you want, and sort of translate them into the real world, whether it's routing boards or trains or anything else. There are lots of challenges that come with that, but also at the same time, if you manage to overcome those challenges, it is truly an exciting time, and you can see actually customers come back and give you great feedback. Customers say, please keep me in the loop for your next release. And we've been constantly improving our product, announcing recently releases, for example, supporting Altium, which is a key standard, and so on and so forth. So I think there is a true excitement in doing things in the real world, even though, of course, it's much harder.
So can you maybe compare and contrast the RL applied to games in this particular scenario? I'm just thinking through some of the differences in the game scenario. You've often got other agents or things in the game, in the environment, kind of respond randomly or probabilistically to the things you do, or at least via some complex function. In this world, you've got your set of components, and unless you're doing kind of deep physics-based, simulations of the interactions between the components, maybe you're not getting into kind of random responses to things. Like, follow down that thread for me.
So one of the key differences is when it comes to gaming, the reward system is very clear. There is a score to maximize, there is an opponent to defeat. So there is full visibility in a sense on what the reward is, which is quite important. So you're already saving a lot of time. You know what's the objective. When it comes to the real world, if I tell you, for example, like, okay, I have this, and this is what we were talking about. I have this complex board with, I don't know, 8 layers and 1,000 pairs to connect. Well, what is the reward function is actually a very good question. You could probably work for years on what is the best reward function you could come up with. So that is one first real challenge. The second challenge is when you design the environment, making sure you incorporate all the elements that are important in actually design, like coding and modeling the environment. If I take the example in logistics that we did and the work we do with railway companies, that is actually not a trivial thing to do. In games, the environment by construction is already given to you and is very clear, not just the reward, but the environment itself. If you're talking about, for example, a complex train network with dozens of thousands of trains operating every day, there could be problems on one railway. What's the consequence of that problem? Just modeling the environment is a challenge in itself. Once in a good scenario, you've modeled the environment. The next challenge is speed. In games, by construction, most games are quite fast because they are, for example, designed for massively online multiplayer games, for example, or things of that nature. So the latencies are in the order of milliseconds sometimes. Building a real-world environment that represents properly the problem that you're looking at, and at the same time ensuring that it's quick enough so that you deploy DeepRL is actually a non-trivial thing. So as you can see, every step of this challenge, which is kind of already pre-built in for games, becomes very tricky in the real world, but also very interesting. And this is also why it's not a surprise that all DeepRL breakthroughs tend to happen on games, because that is sort of the ideal framework to get results.
So going back to my earlier question, is what you've done here that you've trained a model using reinforcement learning that you can then apply to kind of an arbitrary new board that you're presented with? Or is there an element of training that has to happen when you see a new board, or fine tuning or something like that?
It's a bit of both. So the right analogy is what would a qualified human expert do? He comes with a set of knowledge, a knowledge base, and intuition about how to tackle those problems. But of course, he's going to spend time sort of fine-tuning his approach to the problem at hand. So our design philosophy is pretty much the same. There is a pre-built-in experience and knowledge that comes when we tackle a new board, but there is also an amount of fine-tuning. Basically, essentially, the system will learn and experiment on every new board and get something out of it. And when you think about it and you compound those effects, this is how you build a learning system that can progressively tackle harder and harder problems, and together with compute, with more customer served, sort of potentially redefine the standards in the industry. This is our goal with Deep PCB. Today, Deep PCB is in beta format, so it's sort of still learning every day and learning quickly, but still learning a lot. We would like to bring it to a point where the tool is so useful that it is widely adopted by the industry and helps the industry achieve its goals faster and more efficiently. If we manage to crack boards at scale in less than 24 hours, this would change the life of many, many companies operating in consumer electronics, and for the better, because they would be able to experiment with different designs faster, maybe bring products to market that would have been impossible otherwise, because the cost of having a design team work for it for 2-3 months is just unaffordable.
Sure. Can you how do you characterize kind of where you are relative to that goal? How complex are you able to get now, and how long does it take to do a board?
I think it's pretty remarkable what we have achieved already, especially that we are a small startup and do not have access to like large compute. the key thing for us now, if we want to take DeepPCB to its full potential, is really unleash tremendous amount of compute and train on much larger boards. So our goal for this year is really move from like free beta, where we're effectively trying to help customers all over the world and getting feedback in the process, getting them to a point where we can compete with professional product offerings, and ultimately, if we do everything well, redesign the state of the art in the industry. So I would say we're well on our way, probably more than 50% done, but still a lot of work.
Does that mean you're not going to answer my question?
No, I did answer. We're in beta. I wouldn't tell you that our system.
Yeah, no. I'm just trying to. I'm trying to get a
a
sense for, how far along this is relative to both how you measure it. And you talked about kind of the number of components and layers and all that kind of stuff, but also how far along you are relative to that for solving real world problems. Is this something that is, currently useful to someone that wants to route a PCB or not? And how do you know, or how would they know if their problem is practical for what you've done so far?
Yeah, so the great news is we are actually already solving real PCB boards for real customers, and we're very proud of that. Those boards are still small. We're currently limiting in beta to 150 pairs and 2 layers, and we're going to progressively expand that. So this is where we are at the moment. But the good news is that actually we've already received very good feedback from customers from literally everywhere, the US, Asia, and that the system works. So we're pretty excited about it.
You made a comment that one of the limitations is access to compute, or at least you gave the impression that this is kind of constantly, running and constantly improving. Talk a little bit about the relationship with compute and the compute requirement and how you're addressing that.
Absolutely. So if you look at how DeepRL systems work, there is always this concept of accumulating experience through like multiple simulations, gathering this experience to improve your model through gradient descent and iterating again. And if you look at the kinds of amount of compute that you need to really have, for example, a breakthrough in DeepRL, it's quite significant. If you look at StarCraft, for example, like Deepmind actually did spend millions of dollars to crack that problem. Mm-hmm. Today, InstaDeep cannot spend millions of dollars to define the state of the art.
Boards.
So what we're doing actually, we're raising funds, and one of the reasons we're raising a Series B essentially. One of the reasons actually to have enough compute capabilities to push our systems to redefine the state of the art. So there is a real opportunity out there, but compute is a necessary equation when it comes to DeepRL. Of course, you can focus on sample efficiency and the like, but you will not be able to crack those problems with, let's say, a limited amount of GPUs and CPUs available. You will need to have essentially a cloud partner to be able to progress this to the next level. And we've actually done more than that. We actually designed DeepPCB to be fully on the cloud from day one. So every time a customer actually uploads a board, it is solved in real time on the cloud. And so scalability and scalability of learning is essential if you want to have systems that build up new state-of-the-art results. And we're pretty excited about that, and we think this is actually achievable in the near term for InstaDeep, meaning something like a year or less.
We talked a little bit about this kind of notion of, transfer learning, to use that term very broadly, that you're training a model, an agent, and you can, when you're faced with a new board, you can leverage the experience that this agent has experienced, this model's experience with previous boards. We've also talked about, in the real world, like different designs have different requirements. Maybe, one board has specific requirements around noise or, the number of layers relative to others. Maybe, I guess what I'm wondering is if, as you evolve your reward function when you're faced with new scenarios, does that interfere with transferability? Or, can you transfer from one reward function to another?
It really depends of like how far the reward functions are for respective to each other. But in general, transfer learning is pretty robust. So, there is a remarkable ability to transfer knowledge from one problem to another. And this is something we see across the board in AI. And it's the same in printed circuit boards. So if your reward function is not very dissimilar, you will be able to transfer knowledge. If your board is relatively similar to previously seen and solved boards, transfer learning will apply as well. And this is actually a key point, Sam, because this is what makes those systems so interesting. The fact that they learn, but then when faced with a very complex problem, they won't have to necessarily burn all that compute to redo everything again. If you look at how optimization works in many cases today, there is no learning, no memory of what happened. And so, if you have, for example, people, doing optimization on boards or on route problem, or no matter which routing problems these are, well, essentially you're burning compute overnight to solve something. And maybe you're going to come the next night and do the same thing all over again. So the transfer learning part is actually critical. And this is what allows you to keep progressing, as you deploy compute. Sort of this compute is actually more wisely used if you get to results that can improve what you're going to do tomorrow.
You mentioned that you had a spotlight presentation at NeurIPS. Was that related to this work, or is that something separate?
So we were very surprised this year actually to have a spotlight paper at NeurIPS, and this was work done with Deepmind, with Nando de Freitas and his team. And interestingly, we looked at it's a deeper L questions, but around compositionality. How can I, in a bit in the same spirit, but how can I look at certain problems and while I solve simple tasks, use those as sort of like, basic tasks to compose more complex tasks and so on. So at InstaDeep, we're very proud, despite our humble origins, to be able to partner with the world's best in AI when it comes to research and innovation. And one of the things which is unusual about the company is our ability to, on one side, innovate in pure research and in particular DeepRL, but then productize and experiment with this innovation in the real world. And I think that's kind of something pretty exciting because you get to exposed to things that are both intellectually challenging, but also you have a chance to crack real world problems. And so this, it was a big surprise for us in our first collaboration with Deepmind, which for us in itself was a milestone. To get that distinction, which roughly is equivalent to being ranked in the top 2% of all worldwide papers submitted at NeurIPS. So that was one of the milestones of our year.
So can you share a little bit more detail about the paper and the results?
Yeah, so the paper is called Alpha NPI. You can find it on our website, instadeep.com. And what we did is we looked at, in this particular case, toy problems. If you remember, we were speaking about starting with relatively simple things and building up from there. We looked at, for example, the Hanoi Towers problem. So Hanoi Towers is classically, you have those disks, you need to move them from one pole to another, and you need to respect a certain order in which you do this. This is very difficult to solve the Hanoi Towers problem. Let's say a classic DeepRL algo like with DQN or PPO. So Alpha NPI was able to crack that problem using recursion and also using planning. So if you look at, for example, the insights from AlphaGo and AlphaZero, planning is key. So the ability to look ahead and sort of build a tree of possibilities and then decide I'm going to act according to, this path because I really thought about it. Or another way to say it is like system 1 and system 2 in Daniel Kahneman's classification. Well, we've actually applied this, but rather than have just a simple planning algo like a tree that is like a Monte Carlo tree search that is guiding the neural net, we've done multiple layers of trees. So as we have compositionality across multiple levels, we actually are calling trees and doing planning and search across multiple levels, which had never been done before. So if you're interested, feel free to have a look at the website. The paper is there, and also the code is available. We try to be very open, even though we're a small startup. So everything is out there available on GitHub and accessible through our website.
Well, Kareem, thanks so much for taking some time to catch up. It's been great chatting with you as always, and super excited about what you're up to.
Thanks a lot, Sam, and talk to you soon.
All right, thank you. All right, everyone, that's our show for today. For more information on today's show, visit twimlai.com/shows. As always, thanks so much for listening, and catch you next time.